So we've talked about what a force is, that it is a push or pull. So now we're going to look at the different types of forces that we have. We have direct contact, which are contact forces. Basically, matter directly touching other matter, such as wind acting to slow a parachute. So you have the wind directly in contact with the parachute. You have contact forces, friction. When you walk across the floor, your foot is in direct contact with the floor. So the force of the gravity between the Earth and the Moon appears to be what people once called an action at a distance, or at a distance force. These are the opposite of a contact. There is no contact between the two types of matter or objects here. But yet they are able to exert or push or pull and cause movement of an object. So we have our list here. So you have contact forces on the left, such as friction, your normal force, tension, air resistance, and spring, which we're going to talk about further here soon. At a distance forces include your gravity, electricity, and magnetism. This is kind of like the magic forces because you can see them do something, but you don't actually see them directly touch it to cause the movement. This is where we could watch the video on forces at a distance now. Normal forces. The normal force on a body is generally associated with the force that the surface of one body exerts on the surface of another body in the absence of any frictional forces between the two surfaces. Sometimes when we're talking about situations, they'll say friction is present or friction is not. Remember the skate park lab that we talked about when he moved up and down the ramp? Sometimes we would consider friction being there, which would slow him down, or friction wasn't there and he kept going and going and going. When we look at this normal force, the normal force is always perpendicular to the surface in contact. So that means you have is perpendicular to the surface. So here's the surface that this box is in contact to. So our normal force is perpendicular to that. The normal force is an action-reaction force. So here you see the normal force being as an upward arrow. The action-reaction force to the normal force is the gravitational pull going down. So you have the gravity pulling down opposite of the normal. And this is what weight is remember the gravity force. Because weight is measuring the amount of gravity pulling on you, which is opposite of a normal force. When we look at some examples of the normal forces diagrams, we have a box here on the table. You have your normal force, which is perpendicular to the table, going upward, and then you have your weight, your gravity, as the opposite downward reaction force. Same thing with your foot. You have the ground, and then you have your normal force, which is perpendicular, and then the force of the foot due to the gravity. Now, notice that the normal force is written on the bottom in this diagram, but shown on the top in this diagram. That's okay. It doesn't matter where it's at as long as it's opposite of its reaction force. So here on the table again, you have the normal force showing upward and your gravity force opposite going downward, both perpendicular to the table. Now, in this instance, we are on an angle, but yet the normal force is still perpendicular to the surface. So the surface can change. The angle is going to still be perpendicular. So here on the wall, the normal force is perpendicular to the wall. So force pushing against a wall is shown here because gravity is going to pull down, not be sideways. So this is a force pushing, so it's a different, but still the opposing reaction force. Spring forces. Springs are used to make or control forces. The force from a spring always acts to return the spring to its resting shape. You use some springs that you probably don't even realize you use. Some of your binders use springs. Some of your pens and pencils use springs. Some of your doors use springs. So you are using this force and may not even realize it. The force created by a spring is proportional to the ratio of the extended or compressed length divided by the original resting length. We're not going to calculate that. Just know that the size of the spring and the compression of the spring will result in the type of force that you get. So if you stretch a spring twice as much, it makes a force that is twice as strong. So think about a rubber band even, like you pull it farther, you're going to get a harder snap. That's exactly what they're talking about. So if you look at these springs over here in this box, these are two common kinds of springs. Which one of these springs is designed to be stretched? Obviously, you look at them, the one with the hooks, so they can be stretched. The other one that's going to be compressed is the one that can be pushed on. These would be like your bed springs. Okay. This would be like on a swing set if you're hanging something, a jumpy thing or something to hang from. Tension force. The tension force is a force that is transmitted through a string, rope, cable, or wire when it is pulled tight by a force acting from opposite ends. The tension force is directed along the length of the wire and pulls equally on the object on the opposite ends of the wire. They use tension cables on your bridges. Very important that you keep the right amount of tension, otherwise they're going to fall down. You have pulleys that have tension to lift things and move things. The opposite of tension is compression. So tension, you're pulling away from the center. Compression, you're pushing towards. You're compressing it, squeezing it. So this is like a squeeze. And this is more of like a tug of war. But the key thing is tug of war, the tension are equal pulled to the left and right, whereas tug of war, your goal is to try to pull harder than the other. Gravity. The force of gravity on an object is called weight. We talked about this and we looked at this in prior chapters when we figured out what a Newton was. We use gravity on Earth as 9.8, or sometimes you can round it to 10 newtons. Weight and mass are not the same. Mass is a fundamental property of matter measured in kilograms. Weight is a force measured in newtons. So that's the key thing, is weight is a force. Mass is basically matter. It's what it is, what that object is made up of. So weight will depend on the mass, what it's made up of, and the pull of the force on it. The stronger the field, the greater the force also. So the stronger the field, so you're talking gravity can change depending on what planet you're on. It's pretty much going to be the same 9.8 on Earth all the time. May vary slightly, but not enough to even really notice. So if you have this 1 kilogram box being pulled by 9.8 newtons, you increase the mass to 2 kilograms. The force increases and doubles as well. Triple it, the force triples also, because the more mass you have, the more you have to pull downward. So remember that mass is what it's made up of. Weight is the force that's pulling on it. So when somebody says, I need to lose weight, basically what they're really saying is they want to change gravity, the force, which isn't possible unless you go to another planet. What they really should be saying is, I need to lose mass. They want to lose matter. They want to lose their size. But if you change weight, it's not going to change your mass. You go to the moon, you're going to weigh less, but you're still going to be the same mass. So here's a good example of that. You take a 10 kilogram rock on Earth, it's going to have the force being pulled on by 98 newtons. Whereas you take it to the moon, and that same 10 kilogram rock has a force being pulled on it of only 60 newtons because the gravity is less on the moon than it is on the Earth. So here we look at objects and how far apart they are and the size of them will be affected as well with gravity. The more mass two objects have, the greater the force of gravity the masses exert on each other. If one of the masses is doubled, the force of the gravity between the objects is doubled. Now with the distance, if the distance between the objects increases, the force of the gravity decreases. So when one increases and one decreases, we call that an indirect relationship, remember. Whereas you're looking at mass, when the mass goes up, gravity goes up. So that's a direct relationship. So here, gravity is 1/4 as strong as before when the distance doubles. So you can tell that it gets less. So it's indirect. Friction. Friction, friend or foe? Friction is a force that resists the motion of objects or surfaces. Many kinds of friction exist. So we're going to break this down, and you have listed different types of friction. And so friction is going to depend on both of the surfaces that are in contact. Here is an example of a hockey puck. So the hockey puck slides on ice. But right above the ice, right here, there's this thin layer of water, a liquid. And that allows the puck to slide easily. And when you have a fluid or a gas that is the layer between object 1 and object 2, the ice, it's going to reduce the friction. It's going to be called fluid friction. This is the resistance to an object's motion through a liquid or a gas. And when you create a liquid between these two surfaces versus sliding friction, which we'll talk about, sliding friction is greater because you have both surfaces in contact. When you put water in between, it reduces that friction. This is like hydroplaning. When a car goes through a large puddle of water, it loses direct contact with the ground and basically loses what friction it has and reduces it and creates the car to go out of control. Friction is a force measured in newtons just like any other force. Static friction keeps an object at rest from moving. So here we have a free body diagram of showing what this is above. So you're pushing, the guy's pushing the box to the right. Okay, the force you apply is what the guy's pushing against the box. But between the box, right here, the box and the ground, is static friction. It is resisting. It's trying to prevent it. So what this guy's force has to do is overcome that static friction in order for that box to move. Right now, these tables have static friction, which is keeping them in the place on the floor in the classroom. Your book sitting on the desk has static friction. It's keeping it where it's at. Until you overcome that static friction, that object's not going to move. Sliding friction, that I mentioned, is a force that resists the motion of an object moving across the surface. So they're in direct contact with each other. And looking at the surfaces, depending on what they're made up of, so you have to consider roughness, how clean the surfaces are, and other factors of depending on how well they're going to slide across one another. That's why we have traction on our shoes, the grips. You have to have treads. Otherwise, if you ever wear dress shoes and there's no treads on the bottom and you walk on a slippery floor, there's no traction, there's no friction there to prevent you from going. So the greater the force squeezing the two surfaces together, the greater the friction force also. This is an good example of if you push somebody a small child across the floor in a chair trying to push them into the dinner table versus a large adult, it's harder to push the adult because there's more mass, meaning that there's more force, more friction on the chair than a small child. And our other one that we're looking at is rolling friction. So unless a force is constantly applied, friction will slow all motion to a stop eventually. So really, you can reduce friction, but you can't really take it all away. It is impossible to completely get rid of all of it, but it can be reduced. So friction between a shaft and a long pole in a picture over here to the left. So here's the long pole, the shaft that they're talking about, and the machine here. You have direct contact right here, so it's creating friction, which can create lots of heat. So we want to reduce this friction so there's no heat, because heat can be good to be produced by friction, but it also can be bad and cause overheating or fires or burns and things like that. So what they do is they put balls, metal balls in there called ball bearings, to separate the two, and it rolls, makes it roll versus sliding. So you reduce the friction. So any rolling friction, anything that is circular, a ball, a tire, or a wheel that you put between a surface is rolling friction. The rolly desk chairs in the front of the room. My cart up here has wheels on it versus try to move the table versus the cart. The cart's easier because it has wheels on it. A ballpoint pen has a ball at the end to make the writing smoother and easier. There's things that you use. Maybe if you have rollerblades or a skateboard, they have ball bearings in the wheels that cause them to move smoother, creating less friction to make you go faster. So along with the shoes, we have tire treads on tires as well. And the reason we actually have these is because you want the tire to have contact with the ground. Otherwise, like I said, if that water doesn't move out of the way, it's going to create a barrier between here, and then the road's not going to have any contact with the tire, and you won't have any control. Like I said, friction can create heat, and it can be good. And this is friction and energy. So friction changes energy of motion into heat energy. So when you rub your hands together, you ever slide across the floor and get a rug burn, or across the volleyball floor, and that's why they wear knee pads and things like that. So when we look at all forces on an object, all the forces on an object are called the net force. Net means the total, but also means the direction of the force has been taken into account. So think about when you get a paycheck, you get your net pay and then you get your gross pay. Completely different. One's before taxes and one's after taxes. It's always bigger before, and then Uncle Sam gets his portion. So the word net means total, but it also means the direction. So here you can look at this plane, and we have the normal force or upward force of 55,000 newtons going up. And then we have a negative 55,000 newtons going down. So we know that they equal out because, or actually, this is 55 and this is 50. So they don't equal out, so they only cancel out 50, so you're left with 5,000 newtons upward because this negative 2,000 to the left and 20,000 to the right cancel out. So your net force is what's left over, 5,000 newtons to the top, pushing the plane up so it could fly. And we talked about adding vectors, so that's basically what this is doing, is you're considering the weight, which is a gravity, the drag, the air friction, the thrust of the engine, pushing it forward, and the lift, which is caused by the flow over the air. Just kind of like lift force is what we created with the egg in the bottle. And that's exactly what caused the egg to move into the bottle and get out of the bottle. So when the forces act on the same object and they cancel each other out, the net force is 0. So that means that there is no movement. They're in equilibrium. When the net force is not 0, then you know it's going to move. So here, because -10 and -7 are different, you're going to have movement on the object. So when you look at a normal force, they are balanced. The net force is 0. When the net force is 0 on an object, we say the object is in equilibrium, meaning that it's not moving. Again, the net force is created whenever an object is in contact with the surface. So this is the net normal force is the equal strength to the force pressing on the object. So the book sitting on the desk is pushing down at the same force that the normal force is pushing up. Because if it wasn't, then if the normal force was stronger, then the book would actually lift up off the table. If the book was stronger than the table, then the book would sink into the table. So looking at this object here, like you did on your homework, is this object in equilibrium? Well, 4 plus 6 up here equals 10 newtons. And you have 20 to the left and 20 to the right, which cancel each other out. And you have 10 going down, which is your gravity. So because this is 10, they cancel out. This is 20 and this is 20, they cancel out. This object is in equilibrium and will not be moving. And we are to the end of the notes.